All right, well, hello again. Welcome to another physics lecture. Today, or whenever, this lecture is going to be on electric current. So the last lecture, we looked at electricity and sort of the fundamentals of electric fields and the forces between electrically charged objects like electrons and protons. In that lecture was called electrostatics because it was basically looking at things that are electrically charged but that aren't really moving around. Like we were looking at things that became charged because electrons might have moved, but once they did, we said, okay, like you had this rod and this piece of fur and you rub them together and you get maybe a negatively charged rod and a positively charged piece of fur then, but now they're just kind of static, they're sitting there. So the next step is to look at sort of the simplest example of what happens when we want charge to move, when we want these electrical charges to be moving. And that is essentially where I get into current. Okay, so to understand electric current, it's usually nice to use an analogy with a water current, or the movement of water, because it's something we're all a little bit more familiar with. And so first you're going to imagine this scenario where you have, on the left side of the image here, you have this sort of U-shaped container of water, and on the one side there's a larger area, or a larger side of the container, and there's a higher level of the water. And on the right side there's a smaller area and there's a lower level of water. And as you can probably imagine, or hopefully imagine, if you had a setup like that, the natural tendency is for the water to want to flow from that higher pressure area, the side where there's a higher level of water, higher water pressure, to flow towards that lower pressure area until they equalize and are both at the same level. So that's what would naturally happen. But once the water starts flowing, you get a current. You'd say there's a current maybe of water flowing through that bend in the U. But that current would only go for a few seconds maybe until the levels equalize and then they'd stop flowing. So if instead of just having a temporary flow of current, water current here, you wanted to sustain that flow of water current, then we'd have to put in something like a pump, like a water pump. So if we connected a pump to that right side of the U and then output it to the left side, just like the picture here, then we could actually sustain that difference in water pressures, right? Because the current it would naturally want to flow even without this pump. As long as those levels are different, the current naturally wants to flow from that left side to the right side. But if we have this pump and it's pumping at the right high enough rate, it will essentially pump that same rate of water coming through that bend back over to the higher pressure side, and will essentially just keep these water levels at the higher and lower level by continually pumping that water through. Right, so we can think about electric current in much the same way that we think about a water current. Whereas instead of the water flowing, now it's going to be electrical charge that's flowing. But that, just as the water current could be induced or can be caused to happen by a difference in pressure, the flow of electrical current will be induced by a difference in electric potential, or potential difference. So we talked a little bit about potential difference in the last lecture. Feel free to go back and look more on that, and we'll talk about it a little bit more here as well. The same sort of idea follows too, though, that if there is a difference in electric potential, then electric current will flow to try to equalize that potential difference. So like in the first case, if there's a potential difference, or like there was a difference in pressure of the water would flow, or in this case the electrical current will flow and equalize that difference. The same sort of idea follows, though, that if you want to sustain that electrical current, then you have to put something into this system, like a pump in the case of the water, to essentially just sustain that difference in electric potential. So you need a device that actually will, in itself, kind of hold a difference in electric potential. So just like the pump does here, we'll see that other things can do that for electric current, like batteries, electric generators, things sort of like that. All right, so that was still with the picture with water, where you just have the two differences in pressure levels. Here we'll get a little bit of a more realistic picture, getting towards the more realistic picture, or an actual picture, of what it looks like for electrical current to flow. So like I mentioned just a second ago, electrical current is the flow of electric charge, just like a water current is the flow of H2O molecules. And in circuits, like when you plug your phone into the wall to charge, the power lines that go along the street, the circuits inside of your computer, all those, what's flowing in there are electrons. So remember, electrons are negatively charged fundamental particles of the universe. So in most electric circuits, it's the electrons that are flowing. And for the most part, we're just going to think about electrons flowing. We can have other things to flow to cause an electric current, right? It just needs to be a charged thing. So in the case of biological systems, often you have electrical currents that are produced by flow of ions, charged atoms or molecules. But if we take our water analogy picture and push it a little bit further, we start to get this picture on the left here, where water will want to flow around this loop as long as you have a pump that's pushing the water to keep continually causing it like a pressure difference or a potential difference from one side to the other, so that it continually wants to force water around this loop. You might also have a valve. You don't necessarily even need the valve or the switch here, but assume you could stop the water from flowing by closing the valve or opening it up and allowing it to flow again. But the other crucial picture in this, or component in this picture now, is the line that's indicated, which is like if you have a nice fat sort of metal piping for the rest of it, then that metal piping really doesn't impede the flow of the water much at all. It's very big, it just allows water to flow very quickly through it. Whereas this line part is, you can think about it as like a pinched or like a kinked hose, where depending on how pinched it is or how many kinks there are in it, it sort of restricts the water or the flow of water. It impedes the water's flow. But that picture is a basic or a nice basic analogy for how a simple electrical circuit will work. In that picture, you have a pump. You don't need to worry about the valve, but you also have a pinched line that sort of resists the flow of that water in the loop. So go to the picture B here. We now have an idea of an electrical circuit where the pump is replaced by a source to sustain the electrical potential difference between two parts of the circuit. And in a lot of our cases, we're just going to be using a battery, because we all have seen batteries. We usually have a good idea of what a battery looks like and what it does. There's two sides to a battery, sometimes on the top and the bottom. That's where the potential difference is, the electrical potential difference between the top and the bottom of the battery, the positive and the negative side of the battery. Sometimes the battery has the leads of it are just next to each other, like on a car battery. Again, those are the two points where a battery is sustaining a potential difference, an electrical potential difference between So as long as you're connecting to those 2 points, that's sort of like acting as your pump in our analogy here. So we have a voltage source, and again, the switch is like the valve. You could turn the flow of electrical current on and off. You don't even think about it. It's not too much. You don't even really need the switch. But the other key component is now our line is represented by a resistor. And a resistor is just what it sounds like. It's an electrical component that resists the flow of electrical current. So we'll talk more about that, but essentially it's like the pinch line. Right? And in an electrical circuit, if a component has a very high resistance, then it presents a lot of resistance to the flow of current. It makes it difficult for current to flow. And finally, we get to this almost real-life picture where you have a battery that's connected to a light bulb. So now we have a very simple circuit where the battery, again, is our potential difference source. So voltage is another term for electrical potential difference. I think I mentioned that in the last lecture, but it's good to reiterate that. So you can essentially use voltage and potential difference, electrical potential difference, interchangeably. So our battery here is our voltage source, and we're connecting to the positive and the negative side of the battery. We're connecting via, in this case, metal wires, right? Remember, metal is a very good conductor, so it's not going to be a problem for electrons to move along it. So the metal wires here act like those big, wide, metal pipes where it's very easy for water to flow. Here, as long as you have just a nice metal, it's very easy for the charge to flow. And then those wires are connected to a light bulb, and generally, most light bulbs or all light bulbs act as some sort of resistance to current flowing. So that light bulb is taking the place of that resistor there. And then again, the other side of that light bulb is connected down to that negative side of the battery, and we have a complete loop. We have a place where current can continue to flow, and we've got a source, our voltage source, which sustains that flow of current. All right, so a little bit more on voltage sources. So just like sustaining that difference in water levels in the 2 parts of that U-shaped object, if you want to sustain that, then that water needs to continually be pumped from the lower level back up to the higher level. So for electrical current, it's going to be a voltage source that's going to do that pumping for you. And very simple, you can make I've never done this myself, but you can make a very simple chemical battery with some aluminum, copper, and a lemon. So in that situation, I'm assuming the acid in the lemon is pulling ions from the aluminum to the copper, from the copper to the aluminum, and essentially creating an electrical potential difference between the copper and the aluminum, which is then what's going to sustain that flow of electrical current. There's also mechanical generators, which will essentially create the same thing. They'll create a potential difference between the 2 ends of that generator. Somewhat just like a hand crank. We'll talk probably next time more about how you might generate electricity just by turning something. And so we don't need to worry too much about this, but chemical batteries are very common, and our phones have lithium-ion batteries, AA, AAA batteries, they're all chemical batteries. So a brief little bit about that, and like that lemon in the last slide. Essentially, a battery is something that, again, that acts as a pump would in that water scenario. It's our source of our electrical potential difference. And the battery is going to have the 2 leads, the positive and the negative lead. So there's from the positive side to the negative side, there's a difference in the electrical potential. And those leads are generally connected, in a very simple case, they're just connected to these 2 different metals. So in this case, it's zinc and copper. And there is an acid that they're both sitting in. and that acid essentially acts as like a vehicle to pull ions from one of the metals to the other, and in doing so it sort of creates this potential difference between the two metals, which is then the potential difference between the two leads, and that potential difference can then sustain the current to flow if you were to connect them to a wire and to some other elements or other components. Yeah, so a chemical battery or a regular battery that we think of is an example of converting chemical potential energy locked up in pulling things off of atoms and elements, like pulling electrons off or pulling molecules, separating molecules, converting that energy, stored energy, into electrical energy. All right, so let's talk a little bit more about electrical resistance. So keeping in mind that in that analogy with the water pumping around in a loop, that resistance is like that pinched pipe area. And the more resistance there, or the more pinched or the more kinked that area is, the more resistance it's going to present to that pump, so it's going to make it harder for water to flow. Yeah, so whenever you have a circuit, the amount of current that's going to flow in a circuit is not just going to depend on the voltage source that you're using for that circuit to sustain that potential difference. It's also going to depend on the electrical resistance in that circuit. And in general, wires, which are made up of like copper or some kind of metal, are going to be pretty low in resistance. And it turns out that the wider the wire is, the wider the cross-section of the wire, the lower resistance you can have. So a very thin, a very tiny, thin wire is going to present more resistance than a much fatter wire would. And also a shorter section of wire is going to present less resistance than a longer section of wire. Oh. And you can think about this in like the hose analogy, just like, you know, if you have a fat hose, it's much easier to push more water through it than if it was a nice, very like tight, small hose. So there's one reason why jumper cables that you use for your car are generally pretty hefty, pretty thick wires, because you're actually trying to push a lot of current from one battery to the other in order to charge that other battery. So you don't want much resistance between the two batteries, so it's easy for current to flow. So, yeah. Okay, so just some examples of different types of materials and whether or not they're good conductors or bad conductors. And remember again, a bad conductor is what we call an insulator. So it insulates. So, yeah. So any material that has a very low electrical resistance is what we call a conductor. And again, a conductor is something where that easily allows electrical charge to flow. Right? We're talking about electrical conductors now, as opposed to thermal conductors that we talked about in the last section. So some different examples of electrical conductors are like silver, gold, copper, right? A lot of metals. Basically any metal is going to be a good electrical conductor. Some are better than others, but they're all pretty good conductors. It turns out seawater is a good conductor, even though water itself is not a good conductor. And we'll see an example of that shortly. Say a little bit more about why that is. So a material that has a very high electrical resistance, meaning it presents a lot of resistance to the flow of current, is what we call an insulator. Sort of insulates things and doesn't let current flow between them. And yeah, an insulator is just very difficult to get current to flow in an insulator. So some examples of insulators, we got rubber, glass, oil, diamond, it turns out, and dry wood. So you've probably seen things like or if you've ever seen a video of an electrician doing work, especially on like high voltage lines, they're generally wearing rubber gloves, right? Because the rubber is a good insulator, so if there's an issue, you're not going to get a lot of electrical current to flow from whatever component you're working with through the rubber, because the rubber just presents a very difficult path for that current to flow. It's a very good insulator. Okay, so put all these three sort of notions together, right? We have current. This whole lecture is about electrical current and how current flows, similar to water current flowing. And we've also talked about potential difference that sustains that current flow or causes that current to flow, also called a voltage. And then we finally just talked about resistance a little bit, electrical resistance. And it turns out these three properties are related by what's called Ohm's law. And that's it. The current that's going to flow in a circuit is, well, we could say it is proportional to the voltage or the potential difference in the circuit, and inversely proportional to the resistance in the circuit. So hopefully this is, you can start to think with our water analogy why that might be the case, why these relations are the way they are. Right? So like the voltage, again, remember, is like that difference in the heights of the water levels that pushes the water from one side to the other, pushes the current to flow through that U-bend. Right? So, and you could imagine that if there is a much higher or much larger difference in the heights of those waters to begin with, there's a much larger pressure difference, the current's going to flow even faster through. Right? So that's why the current is going to be proportional to a voltage. Right? But, well, in that analogy, the resistance is essentially you kind of maybe put stuff into that U-bend area where you kink it down so you make it more difficult for the current to flow. So in that analogy, you have a difference in water level, that's the voltage. But if you add resistance into that U-bend area, you put screens in there, and just kink it down, you squeeze down that cross section, right? That's adding resistance to that system so that there's going to be harder or less current is going to be able to flow from one side to the other. So that's why the current is going to be inversely proportional to the resistance. And in case you were wondering, we haven't worried too much about units, but the unit for a current is what's called the ampere. These are all named after people who did work in these areas or discovered certain things. So ampere, and we just use symbol A. The symbol for voltage, or the unit for voltage, is kind of a confusing one. The unit is called a volt, and we use the symbol V. And finally, for resistance, the unit is called an ohm. Same guy, Ohm's law. And we use a symbol that's a capital omega. It's a Greek letter. All right, so let's see maybe an example of resistance in a circuit, and also how that resistance can be changed a bit. As I mentioned before, salt water or seawater is actually a pretty good conductor, whereas pure water is not a good conductor. So in this demonstration, somebody's connected a circuit. So in the video it's not as easy to see, but on the far left side of the image there's a power source, which is the source for our potential difference. And that source is connected to a light bulb, and then the other side of that light bulb, instead of going directly back to the power source, is connected to these little metal prongs, which are just dipped into a bowl of water. So get one prong in, get another prong on the other side of the container, and that side is then connected to the power source again. So there is a loop for electrical current to flow, but it needs to be able to flow through the water. in order to actually go around this whole kind of circuit. So water itself, like I said, is not a good conductor. It's an insulator. So when you connect this circuit to begin with, and you just have the water there, there's no current that's going to flow, and you can see that because the light bulb doesn't turn on. So when current flows, it will heat up the filament in the light bulb, and you actually get it to glow, and you see that visible light. So to begin with, there's no light, so there's no current flowing, and very quickly after the person takes some salt and puts it into the water, you see the light bulb start to illuminate. And the reason is that salt in the water is, well, they say maybe it's impurities, but essentially the salt, it easily creates ions, charged molecules, electrically charged molecules, and those charged molecules can then conduct the electricity, or are able to then conduct the current, the electricity, in the water. So water without salt, insulator. Water with salt, conductor. So let's see. So water, and now it's going to add the salt, doing nothing else but adding this salt into the water. Ta-da, light bulb goes on. So there you go. Resistance of water, very high. Resistance of salt water, pretty low. Alright. So just as a bit of a, not necessarily an aside, but something that's interesting about the flow of current. If you ever talk to an electrician or anybody who works on electrical circuits, especially high voltage circuits or high powered circuits, they'll tell you that it's not voltage that's an issue when it comes to electricity, it's current. So, or another phrase was, it's not voltage that kills you, it's the current. Right? So if you think about it, there are many examples of things that have very high voltages, very high potential differences, but are not deadly, right? Or not very particularly hazardous. So you have, like electrified fences, where it could be tens of thousands of volts, which is a lot of high voltage. But if you touch them, you're going to get a good shock, and it's going to be painful, but it's not going to kill you, unless maybe you have some very serious heart problems already. Similarly, like tasers, they're called non-lethal devices because they're meant not to kill you. They just use a very high voltage to sort of shock your system and seize up your muscles. So it turns out that you can interact with very high voltages and still be okay. But it doesn't take a lot of current to do some damage, do some very real damage. So one way to think about that is that, going back to the idea that the voltage is really just like a potential, it's causing a potential difference, but in that sense it's a potential for current to flow. And the amount of current that's going to flow depends on how much resistance is presented to that voltage source. And the thing that's really moving, the thing that's going to cause damage, is that flow of current. It's the electrical charges flowing, moving back and forth and moving in one direction. It's that physical movement and collisions that might happen that are going to be a problem. Right? So that's why the current itself is really the issue. So it turns out that when you're talking about electrical currents, it only takes maybe a thousandth of an amp or a milliamp before you can feel that amount of current flowing. Then 5 milliamps, I guess, is where it maybe gets painful. 10 milliamps can cause muscle contractions, can cause spasms, or your muscles to seize up. It's like 15 milliamps can cause loss of muscle control. And 70 milliamps can cause disruption to your heart, and, well, if it lasts for any sustained time, it could be fatal. So these numbers, you don't really have very good of an idea, but or I guess a measure of things to compare it to, but in like a, well, if you just have a normal AA battery and you're connecting it to a light bulb, like we saw in one of the last pictures, there's probably a few milliamps of current flowing. Right? So you're in that range where maybe you could actually feel that current. You'd probably feel it if you touch the wire or touch two parts of the wire. And it might be a little bit painful, but it's not really going to do that much. Versus the current that could flow out of an electrical socket or an outlet could be much higher. Some of the very fast battery chargers or cell phone chargers now are up to like an amp of current, right? Which is a lot of current actually, right? So when we're talking about current in terms of amps, milliamps is kind of like a regular medium-ish kind of mid-level-ish amount of current, whereas an amp is actually a very substantial amount of current. But even saying that, it doesn't take more than 7/10 of an amp to start being potentially very dangerous. All right, so how about a question for you? So in the last section, I didn't talk about it as much in the last slide, but it did mention, or it did show on there that your skin, when it's dry, has a fairly high resistance. It actually has about 100,000 ohms resistance, right? Meaning that, well, it's going to be difficult for current to flow along your skin or through your dry skin. So let's say that your skin has that 100,000 ohms of resistance. How much current is going to pass through you if you were to touch a 120 volt electrical socket? So the sockets, the electrical outlets in your home are generally operating at a potential difference of like 120 volts. Right? So that's why I would pick 120 volts here. And then compare that to what current would flow if you only presented, say, your skin was maybe wet, so the resistance was dropped down, and it only had a resistance of, say, 100 ohms. So we would just use Ohm's law that we saw a couple slides ago in order to calculate the amount of current that's going to flow. It's a fairly simple calculation. Give it a try. Alright, so there you go. So Ohm's law says the current that's going to flow is equal to the voltage divided by the resistance. So this is our voltage, 120 volts, divided by the resistance, 100,000 ohms. We would get 0.0012 amps. I think that's correct. Or 1.2 milliamps. So looking back on that last slide, this is roughly to the point where you're going to feel it, and probably not much more than that. You get a jolt, as long as you aren't stuck to it and you don't hang on for too long, then probably not going to be much more than just a startle, or just to startle you. However, if for some reason your body's resistance, your skin's resistance dropped down to 100 ohms, do that same calculation, you find that 1.2 amps of current are going to flow out of that light or that outlet and through your body, right? And that's well above the area, that region is going to be dangerous. So it'll probably kill you. So be very careful when dealing with like electrical sockets, it's one of the reasons. It's good that dry skin has a fairly high resistance, but if your skin is wet, then it conducts current a lot better. It has a much lower resistance. So, yeah. Okay, so for the most part, the current that I've been talking about and telling you about is what we would call a direct current, or a one-way current, essentially. So like in that analogy, that water analogy, the current that's flowing, the water that's flowing there, is always flowing in one direction. It's flowing from that higher side to the lower side, and then the pump is pushing it back from that lower side to the higher side, right? So it's going in this continuous loop, same direction. And the same follows for most of the examples we looked at with electrical current. You have a battery, it has a positive and a negative side. Those positive and negative sides are always the same, there's always a negative and positive. And you connect it to a circuit, to a light bulb, say, the current's going to flow in that circuit, and it's going to keep flowing in the same direction. So that's what we would call a direct current flow. It turns out there's another kind of current flow, which is actually very common because of the type of current that flows in our power lines, over electrical sockets. But we're not going to worry too much about it. It's much more difficult there's a lot more complications involved. So for the most part, we're just thinking about direct current. But since it is such a prominent thing in the world, it's good to actually at least have some idea about it. And that is what we call alternating current. So instead of current flowing in a single direction, in the same direction in the loop, we would have current that flows one direction in one moment, and then the other direction in the other moment. So if this was back to that water analogy, right, you have the difference in heights of this water, and naturally that water wants to flow from the higher to the lower side. Our pump is pumping water from the lower side back to the higher side. For an alternating current, it would be like our water pump is just being reversed in direction every, I don't know, second, something like that. It doesn't really matter what time it is. It's just the fact that it keeps reversing directions, right? So at 1 second, the water is going to be flowing from the higher side to the lower side, like it normally would, or like we did in the last example. But you flip the pump around, it actually has enough, as long as it's strong enough, it's going to reverse the flow. It's going to push water from the lower side to the higher side. So in an alternating current circuit, you have a current that's flowing, but now it's flowing in some of this back and forth motion. So some examples of, well, I've already talked about them, but for DC, your computer, your phone, your most devices that you're going to use are working on DC current. But, like I also mentioned, the power lines that we all connect to in the outlets are running on AC current. So one of the things that the plugs, when you plug your phone into the wall to charge it, one of the main things that little box is doing is converting that AC current to a DC current that will charge your battery. It's also changing the voltage levels a little bit because they're not set up for what your phone will want. Now let's look at a little visualization here. So here you go, a very simple picture of a DC circuit versus an AC circuit. In a DC circuit, just imagine having a battery. It has a positive and a negative side, and those positive and negative sides don't change. So what it's doing is continually pushing current around the same direction in that loop, in that current loop. Versus our AC current, where usually we use just a circle and a symbol with a little sine wave to show that it's going up. It's going positive at one moment, negative another moment. But that's just a symbol you usually use for AC voltage sources. But we see that the charges in this current loop, in our AC current loop, are going clockwise one moment and then counterclockwise then clockwise again, and then counterclockwise, right? So this is what we mean by alternating current. And it turns out each of these are capable of transferring power. Right? They are each being used or useful, but some are useful and more useful in different situations. So these are two main kinds of electrical current. Okay, so just a little bit more about DC, direct current, versus AC, alternating current. DC current is generally pretty easy to produce with batteries, and generally you're also going to be working at lower voltages. So DC current, just think about AA, AAA, D batteries. AC current is used for power transmission generally, and the reason being, in a nutshell, is that when you have current flowing, alternating current flowing versus DC current flowing, you actually end up getting less power loss along a transmission line. So it turns out that if we did use DC current in our high voltage power lines, most of the power that's generated at the power plant would be dissipated before you could even use it at your home. So AC, think about power lines or outlets, power outlets, or wall sockets. All right, so let's think a little bit more about current, and more like the sort of atomic picture. What's going on a very small scale in terms of current? So I told you before that for the most part when we think about current, we're thinking about the flow of electrons. Those are the things that are easily movable in atoms and materials, and so in general those are the things, they're charged, so those are also the things that are going to be like the H2O molecules in a flow of water. Those are the things that are flowing in a current flow, electric current flow. So just like atoms in general, we talked about this before, electrons, just like atoms, are in constant motion. They're perpetually moving around. And in a conductor, one thing that makes it a conductor is that the electrons that are part of the atoms that make up that conductor, generally metals, those electrons are pretty free to move around the entire conductor. Right? They're not necessarily contained to be part of one atom or the other. They kind of get shared by the whole material. So in a conductor, you can sort of think about the electrons as it's like being their own kind of gas almost, right? They're tiny little things, they're moving around constantly, they're doing all this random sort of stuff. In electric circuits, or if you want current to flow, then we can imagine a little chunk. This is supposed to be a little piece of wire, right? It's part of a much longer wire. And it's a metal wire, so it has these electrons that are moving around freely. So that green line is like just showing that electron doing this random sort of motion. Now, if we were to connect that wire to a Alright, so I'm realizing this might be going a little bit long. I'm going to try to speed up just a little bit here. Let's see how that works. Okay, so given that materials have resistance, and that resistance, if you think back to the last slide, it is resistance to those electrons being able to move freely through a material. And more specifically, that resistance is essentially those electrons bumping into things in the material. Right? So things that are impeding the flow of those electrons. And when electrons bump into things, well, they're going to give energy to those things, right? So imagine electrons hitting atoms or molecules in the material they're trying to move through or move in. When they hit them, they give those atoms energy. Those atoms start moving more. What that means is that the atoms are heating up, they're increasing their temperature, and so we get things like the filament in a light bulb heats up enough that it starts to glow. You get visible light. You can have things like a toaster where the electrons are heating up the metal in the toaster enough that those glow and give off light, visible light, but also infrared light that cooks your toast. Yeah. So let's see an example of that. All right, so it turns out you can use this, well, it's called ohmic heating, because your ohm is another name for the unit of resistance. So ohmic is like resistive heating, or essentially using current to heat things. It turns out if you run current through something like a hot dog, enough current, then you can heat it up, you can cook it, right? Not necessarily the most efficient way to cook a hot dog maybe, but it can be done. And it can be done in spectacular fashion. Let's see a video of that. So in this video, it starts out right away with this picture of the hot dog, but essentially the hot dog's connected to two sides of a circuit. It's put into a circuit, so the current's going to flow through it. And this video is all about safety, dealing with very high voltages and very large currents. So you're not just cooking this hot dog, essentially it basically explodes. Right? So the current passed through that hot dog. The hot dog has some resistance. That's the electrons bumping into all the atoms in the hot dog. So it dumps a lot of heat into that hot dog, and if it's a very high current, it will dump heat very quickly and heat it up enough to combust in this situation. Okay, so when we're talking about electrical current flowing, or in the last part about ohmic heating, a lot of that stuff comes back to, well, if we want to talk about how much energy is being transferred by that current flow, then we might talk about how much energy is transferring during a certain amount of time. Right? So how much energy do you flow over a second or an hour or a day? So we're talking about the rate of energy flow, or the rate of energy being moved or delivered. That's what we would call power. And in terms of electrical circuits and electrical current, you can calculate the power that's being delivered or that's being expended, depending on how you want to look at it, by multiplying the voltage difference that's being applied to a component, like a light bulb, and the current that's flowing through that component. And the unit for current is a watt. We use W for short. So as an example, you have a light bulb, an incandescent light bulb that's maybe a 100-watt light bulb, and it's meant, as it's shown in this picture here, it's meant to be connected to a 120-volt source. So how much well, if you rearrange this relationship to say, you can say that the current that's going to flow is equal to the power that's delivered divided by the voltage. And in that way we could find out that in this light bulb, there's going to be 5/6 or about 0.8 amps traveling through this light bulb. And so if you were to connect this light bulb to a European circuit, where in Europe their voltage standard is 240 volts, so twice what our voltage standard is here. If you connect it there, that's double the voltage. Turns out you're going to get, you get half the current flow. You're dividing the power. It wants to sustain that 100 watts of power. You divide it by 240 volts, and you get about 0.4 amps. Okay, So we've talked about electrical circuits, and the very simplest circuit is essentially a voltage source, a source of electrical potential difference, connected to a resistor and in some sort of loop. So that's like our picture up here at the top. You have that water analogy, and then you have a much more or closer depiction of an electrical circuit. But essentially you just need a voltage source and you need some kind of loop, and that loop will present some resistance. So that's the simplest kind of circuit you can imagine. Something that I've kind of alluded to, but it's necessary for a circuit to be, to work, to do anything, is that there needs to be a closed path for current to flow through that circuit. So for instance, in the picture up here, when you open that switch, there's no longer a path for electrical charge to flow, for electrons to flow around the loop. So you've broken that circuit, right? You're no longer going to get charge flowing. You say it's a broken circuit or an open circuit. Right, so the next two slides are just going to look at some common ways of making more complicated circuits, how you build circuits from just that simple idea of a voltage source and a resistor. Right, so one of the ways is what's called a series circuit, the other way is what's called a parallel circuit. And I should say also that we're only talking about resistors in circuits right now, but there are a few other components that make up basic circuits. Like we mentioned capacitors in the last circuit. That's also another fundamental component of electrical circuits. But for the most part, we're just looking at resistors right now, thinking about resistors. Okay, so a series circuit is essentially a circuit, or part of a circuit, could be a loop of a circuit, where the same current is going to flow through every element in that part of the circuit, or in that loop of the circuit. So that's to say that there's no junctions, there's no splits in your circuit. There's a single path for a current to flow. So we could depict it here like if you wanted to connect 3 light bulbs in series, you'd say we connect them in series. You would just connect them essentially one after the other. You connect one end, say a voltage source to one end of the light bulb, then you connect the other end of the light bulb to the next light bulb, and then the other end of that light bulb to the next light bulb, and the other end of that light bulb back to the voltage source. So in this picture, if you imagine it again as the current flowing as water flowing, there's one path for that water to flow. There's no splits where that water is going to split up and some's going to flow one direction, some's going to flow another direction. All of the current's flowing in the same one. So in a series circuit, since there is only that one path for current to flow, if you disconnect any component in a series circuit, the whole circuit's broken. There's no longer a path for current to flow in that circuit. So the other main type of circuit that we build circuits is, like I said, a parallel circuit. And in a sense, the components in that circuit are parallel to each other. So the sort of fundamental property of a parallel circuit is that there are splits in the circuit. So there are junctions where current flows in and splits, and some of it will flow one direction, some of it will flow another direction. So for components to be in parallel, you'd say these light bulbs are in parallel. You have essentially one side of each of these light bulbs, say the left side of this light bulb here, or the left connector of this light bulb, are all connected to the same point of the circuit. So that point A that's indicated is that junction in the circuit, and that's where current's going to flow, say, from the battery, but once it gets to A, that current splits and flows through those different paths. So some current flows through the top light bulb, some current flows through the middle light bulb. In this picture, the switch is open to the bottom light bulb, so there's no path for current to flow there, so no current's going to flow there. But the top and the middle light bulb, we would say, are in parallel with each other. And if that switch was closed, the third light bulb would be in parallel with the two as well. They would all be in parallel. So all of one side's connected together, all of the other sides connected together. So you take any components, like light bulbs, and you sort of connect them, each of their sides together. The nice thing about a parallel circuit is if you disconnect one of the light bulbs or one of the components, like in this picture here, it doesn't break the whole circuit. It only breaks that, that part of the circuit. Right? So like if I open that switch, that light bulb is going to go off, but the other two light bulbs aren't. There's still continuous loops for current to flow from the voltage source through the light bulb and back to the voltage source again. Okay, so a couple of questions for you about these circuits. For one, how would the brightness of these light bulbs compare if they're identical light bulbs, meaning they each present the same amount of resistance to current flowing? Which light bulb would draw the most current? What would happen if light bulb A was unscrewed, and what happens if bulb C is unscrewed? So hopefully you can answer at least the second or the last two questions. The first one might be a little bit more difficult, and the second one might be kind of difficult. But if you take a minute, pause, and try to answer each of those questions. Okay. So it turns out that light bulb C is going to be the brightest light bulb in this setup. And one way to understand that is, again, to think back on our water analogy. So in this case, it's like we have a pump here, and that pump's connected to these pipes, and the pipe splits at some point. Some of it goes, a path goes up along AB, and another path goes through C, and then those pipes recombine to go back to the pump. And these light bulbs are resistors, so they're resisting the flow of current. Or back to our water analogy, they're like kinked lines, right? They're like tight hoses that are kinked. So for A and B, since they're on that same path, they're each presenting resistance, and the resistance of them is combining in a way because they're in the same path of that water flowing. Versus C, there's only one of those resistors there, so there's like one section of kinked line, and it's presenting less resistance than A and B are. So essentially, when water gets to that junction, if it was going to flow around here, it would flow up, it would flow to that junction, and it would be harder to flow through A and B because there's more resistance there than it would be to flow through C. So more of that water is going to flow through C. Same thing happens for electrical current. There's more resistance up on that AB path than there is on C, so more current is going to flow through C. More current means, well, essentially just means brighter light bulb. More current, heating up the light bulb filament more, giving off more light. So that's related to the second question, which light bulb draws the most current? That would be C, for the same reasons we just said. What happens if light bulb A is unscrewed? Well, since A is what we would say A is in series with B, if I take light bulb A out, then essentially I've opened up the circuit on that top part of the circuit, and there's no longer a path for current to flow through light bulb B. So light bulb B would go out, but light bulb C, there's still a path for current to flow from the voltage source through C in a complete loop, so C would stay on. And what happens if you take light bulb C out? Well, then you would just break that component of the circuit, but A and B are still going to be lit because they still have a complete path for current to flow through them. Okay, so as it turns out, the electrical wiring in your homes and in buildings and such is connected essentially in parallel circuits, so that you plug in a lamp to an outlet, and you plug in a battery charger to the outlet, you plug in your phone, plug in a bunch of things to the outlet. They can all be on or using electrical power, they can all be drawing current. Or you could pull one out, you could take it out, and it doesn't affect the other ones. Right? So that's an indication that just like in the other circuits where you had parallel components, if you took one out, it didn't really affect the other ones. So same thing happens in your house. If you unplug one appliance or one thing, it doesn't affect the other ones. So all the circuits in your home are parallel circuits. And we could draw a picture of those circuits, maybe like something like here, where the lines here at the very bottom go down and connect to, eventually connect to a power company that's supplying a potential difference for you. They're supplying a voltage source, or acting as a voltage source for you. And all of these components are connecting in parallel with each other. So what that means is that since they're in parallel, they can each draw sort of their own current. They can siphon off current along the way. And since they're not in series with each other, they're not. When you add more and more, you won't get less and less current because you won't have a buildup of resistance in a single path. So that allows you to actually keep connecting more and more components and drawing more and more current, but that can become a hazard because as current flows through the wiring in your walls, if it gets very, very high, then remember that current is just electrons flowing, so the electrons are flowing, and you're going faster and faster, and there's more and more of them moving as the current gets higher, then they're going to be running into the material of the wire, and also generally there's plastic coatings around the wire to insulate them, but they're going to be hitting those plastic coatings too. And if it's a lot of current, then those electrons are going very fast. They're going to heat up that wire by smashing into all the atoms that make it up and the insulation around it. Heat it up enough, you can melt that wiring and, well, spark to something else. You can cause an arc to something, you can cause a fire. So we don't want incredible amounts of current to be flowing through our house, essentially for that reason. This is why we have things like fuses and circuit breakers. Yeah, so fuses are essentially electrical components that are meant to break down. They're designed to fail when there's too much current flowing through them. So we have a little diagram of a fuse where you connect it to a circuit or put it inside of a circuit so that you connect one side over, say, at the top there, the other side at the bottom here. So current that's flowing in the circuit will flow through that fuse, but the material that's made up of the fuse is designed to heat up through that ohmic heating that we've talked about. And when the current's very large, it heats up enough that essentially it melts and it breaks the circuit. It opens up the circuit so there's no longer a connection for that current to flow. That's one kind of, or one way of protecting against too much current flowing. Fuses, you see them in cars. It's a very common place to see fuses. Other places too, in electrical components or devices. There's fuses often. The other way, or another main way of stopping too much current flowing, is with circuit breakers. And circuit breakers work a little bit differently, where essentially they're like a switch, so it can be opened and closed. Right? And generally when everything's working fine, it's closed, but it utilizes another property of electricity and magnetism that we haven't talked about yet, and we probably will at some point later on, just a lecture maybe. But essentially when enough current flows, it causes a magnetic force to arise that pulls that switch open. So don't worry too much about how that works. I think we'll probably talk about it next time. But essentially enough current flows, it's like a magnet switches on and it pulls that switch open. Right? So then you've broken the circuit, no more current flows, right? Stopped current flowing. And circuit breakers are nice because unlike a fuse that it's designed to break, so it needs to be replaced once it actually is used, circuit breakers have that switch, so you just go ahead and flip that switch back and you close the circuit again. If you had this experience where you actually go out your home circuit breaker, you know, the lights have gone out in some room or something like that because you're had a space heater and a hair dryer and a microwave and all this stuff going on in the same circuit, go out and switch that circuit back, I would suggest rethinking about how many appliances you got going at that time, because if you continue doing that, you're just going to keep flipping that circuit breaker, keep having to do that. And it's dangerous too, because all that current flowing means you might be doing damage to the wiring in your home. Okay, so finally, just last question, way to check yourself here. Go back to that way of calculating power, and maybe, hopefully, you can see how to utilize that to answer some of these questions about connecting the hairdryer to your power outlet and how much current is drawn there, and then decide how many hairdryers you can connect before you start blowing a fuse rated for 30 amps. Alright, so hopefully you look back at the relationship for power, voltage, and current, and do the same thing we did in one of the other questions, where you rearrange that relationship, essentially divide both sides of that equation by voltage, so that we now have current. The amount of current that flows through a component is going to be equal to the power that is delivered to that component divided by the voltage that is applied to that component, the potential difference being supplied to that component. So if we plug in these values, you see that a 1200 watt hairdryer plugged into a 120 watt or 20 volt power source, voltage source, is going to draw 10 amps. 10 amps is quite a lot of current, remember? Even 1 amp is a lot of current. So things like hairdryers tend to draw a lot of current because, for one, they're using that current to heat up heating elements, so that you actually heat the air and actually drive some kind of fan or pump of some kind to move that air too. And so hair dryers can use up quite a lot of power and draw a lot of current. So what that means, if you have a 30 amp fuse or a 30 amp circuit breaker, something's going to open, a circuit breaker is going to open once 30 amps are flowing. That means you could plug in 3 hair dryers and you're going to reach that limit. It only takes 3 hair dryers going to blow a 30 amp fuse. Okay, so that's it for our electrical current lecture. I keep saying a lot. I'm trying not to, but it just happens. So the next lecture, we're going to start talking about magnetism and probably combine that with induction, because we only have so much time. So just a little preview, and that's it. That's all I got. So best wishes to you all, and I'll see you next time.